sing yawn.
So it's a song yawn? Wonderful. Okay, so relative extrema, meaning relative minimum, relative maximum, and then graphing polynomials. Just a reminder, we will be spending the entire class period on Monday graphing, sketching, using the derivative and so on. So it's very important that you're here because it's on the quiz. Okay, so you kind of need to be here. All right, so a function f is said to have a relative maximum, okay, a relative maximum, okay, also abbreviated as REL max, okay, and you can use this. This is recognized on the AP, so I will recognize it in class. Remember, less writing, less hand cramps. If at some given x sub 0 value, if there is an open interval containing that value, and f of x sub 0, meaning the y value, is the largest value in that interval. Okay? It's the largest value. So basically you have to look at your numbers, right? Okay, and then f is said to have a relative minimum, also abbreviated RELMIN, relative min, if your y value is the smallest value in that interval. Okay. If the function has either a relative maximum or a relative minimum at some given x sub 0 value, then f is said to have a relative extrema at that given x value. Okay, whether it's a relative max or a relative min. Okay, so again, that's a definition. Basically, you're looking for the picture that you have when you graph something in a calculator, let's say on a 10 by 10 window. You're looking for the relative or local max and local min. You did talk about those in Algebra 2. So you could have another relative min or max, but if it's not within the window that you're looking at, the domain restriction, then it really does not apply to you. It's what you see when you graph. Bless you. All right, so in this example, what we want to do is describe the relative maximum, relative minimum, or any relative extremum, meaning either max or min, at a given x value. And really what we're looking for is if we have a relative max, this would be like a hill, okay, and our minimum would be like a valley, okay? So if we're looking at our first graph here, we are looking to see if we have any relative extremum. All right, so first of all, do I have a relative max, meaning some kind of hill in this graph? No. So in this case, we would say no relative max. And what about a relative min, meaning do I have a valley?
Yes, you do.
I do. Where is my relative min? Where x is equal to 0. That is correct. Okay, questions on this one? Okay, pretty straightforward, right? Okay, take a look at our cubic graph here. Do we have any hills or valleys?
Both. Well, like half of one. So.
How would you describe this right here?
What?
It is an inflection point. Why is this an inflection point? This x cubed is concave down here, concave up. But is this really a valley or a hill? Like, look at this. Is this a hill?
It's like a gene splice.
This is a valley. In this case, what's the slope here at this point? 0, okay? There is no definitive, even though there is a change in concavity, there's a slope of 0, there's a horizontal tangent line here, there is no relative extremum in this case because of the way that the graph is drawn. So no relative extremum, which is plural. What I'm looking for here in terms of a hill or a valley is something that's very specific and very obvious. Okay? So in this case, do we have a relative max? Yes, where x is equal to negative 1. What about a relative min? Where x is equal to 1. Okay. In this next example right here, what we're looking at is a visual of, let's say the domain restriction, we'll say, is negative 4 to 4, right? We have no idea what's happening beyond. Okay, it looks like nothing's happening, but we don't know. Okay, so in this case, if I'm looking at the graph, what can you tell me about this value and this value? Do they both classify as valleys? Yes. So because we're not talking about absolute, meaning the only one, okay, you can actually have more than one relative or local min and more than one relative or local max, because it's the number of hills and or valleys that you're looking at in that picture. So if you're talking about a relative minimum, the relative or local, meaning in that picture, minimum that we see occurs in two places. X is equal to what? Negative 1 and 2? So that's the biggest thing, is that you can see two of these in your picture. One here and one here. Okay? In terms of a relative max, we only have one. Agree? X is equal to 1. Okay, questions on these four graphs before we go to the last one, because the last one is a little bit unique. Okay, let's take a look at this last one. What is unique about the cosine of x? Say again? It continues on in either direction. That is true. So that means my domain goes from negative infinity to positive infinity. So if I were looking at just y is equal to the cosine of x, meaning, this is going to bring back some memories, no phase shift, right? No period change. Okay, it's just a plain old cosine of x. Amplitude of 1, period of 2 pi if I were sketching just one cycle. Okay, in this case, as Adam said, the graph goes on infinitely. So if I were looking here and I asked you how many relative max values do you have? Just in this picture, how many do you have? 3. 3 relative max values. But because Adam pointed out that the graph continues infinitely, can we make a generalization about the maxes for the cosine of x? Because aren't they going to occur in the same spots given some general equation, function? Yes? Okay, so first of all, here we're looking at what? X is equal to negative 2 pi, x is equal to 0, x is equal to 2 pi. So how could I generalize that for a relative max? Say again? You're right. 2 pi, we typically use what? K or n? So a relative max would occur at 2 pi k. You just stay away from x and y, because those are standard graphing coordinates. So then let's look at our relative min, because it's going to be a little bit different. Our relative mins occur at negative pi, pi. So what's the next one going to be? Pi k. No. I don't know. I'm listening. Well, where's the first one? Let's talk about it in terms of positive. It starts at pi. So where's the next one going to be? Yeah, you got to add 2 pi, right? Because it's going to occur at 3 pi. And then the next one's going to be at 5 pi, and so on. So can we say pi plus 2 pi k in terms of revolutions? Okay, so this one we had to think a little bit about, because we know that this graph goes on infinitely. It's not something that we can assume. Okay, but typically you would be given a domain restriction. For example, from negative 2 pi to 2 pi. That's what you would be looking at. Okay, so just make sure that you read. Okay, questions on relative minimum or maximum? Okay, relative means we are looking at the picture that we're given. We can have more than one. Okay, so here, the relative extrema for the 5 examples that you just saw occur at the points where the functions have horizontal tangent lines. What does that mean? Horizontal. Say again. The slope is 0, so that means f prime is equal to 0. Right? So let's look. Here, f prime is 0. This could not be classified because this was an inflection point, so this was just a little bit unique. F prime is 0, 0. Everybody good? Okay. So what you need to understand is that relative extremum can also occur at where a point, at a point where a function is not differentiable. So you remember we talked about those? What were those two unique, actually 3 unique situations? A cusp, vertical, okay, vertical tangent line, that won't occur for this, but yet that is one of the scenarios that I'm talking about. And then the last one is the sharp point. Yeah. Yes. Okay. So in general, what we would define a critical point, okay, also a critical number. So these two terms are interchangeable. We called them critical numbers when we were calculating. So this would be the same thing as a critical number or critical point. Okay. For function f to be either the point in a domain where f has a horizontal tangent line or f is not differentiable. So this is like a general term, like if I said to you polynomial. That could be a ton of things, right? Okay, so this is a critical point, meaning the slope is equal to 0, meaning the derivative is equal to 0, or you do not have a, that function can't be differentiated at that point, meaning this has a horizontal tangent line, agree? Yes? So this is considered a critical point, agree or disagree? Okay, so critical point. Here, horizontal tangent line, critical point, yes. Horizontal tangent line, we have determined critical point. Now, the other portion of that definition says that f can also be a critical point where the function is not differentiable. So what would you classify this as right here? Look at the graph. A cusp. And we know that a function is not differentiable at a cusp. However, could this be a relative max? Based on the definition, this is a critical point. So this is a critical point, and so is this right here, critical point. Okay, so critical points are considered, it's a broad term, okay? But then you also have another definition to distinguish between these two. Okay, I can't just say, oh, this is a critical point, this is a critical point, yay. All right, so then there's a ton of critical points on this graph. A stationary point is where f prime is equal to 0. Okay, so a stationary point is a subset, meaning, I said polynomial, that's a very general term, quadratic. That's more specific, right? It's x squared. Or cubic, it's x cubed. Everybody with me? Okay, so this is a subset of a critical point. So if you're looking at these, this right here is definitely a critical point, but this is also considered a stationary point because you can take the derivative and it's equal to 0. Check? Okay, so this is also a stationary point. What about here? Critical point and stationary? Yes. Critical point and stationary. No, you can't take the derivative here. Critical point and stationary. Stationary? Yes. Okay, does everyone understand the difference? Okay. A theorem that we have here. So it says, suppose that you have a function that is defined on an open interval containing some given x value. If f has a relative extremum at some given x value and that value is a critical point, okay, what they're saying is that f prime of that value is either equal to 0 or not differentiable. It goes back to this critical point, which is what we just talked about. This is just the formal definition. So they're saying that you have a given x value over that interval that you're looking at on the graph, and they're saying that that point, x sub 0, that x value, is either a critical point and or a stationary point based on the definition. So if you can take the derivative and it's equal to 0, meaning you have a horizontal tangent line, you know it's both stationary and critical. We determine that up here. Or if the function is not differentiable at that point, it's just considered a critical point. So it's just reiterating what we talked about on the graph. Okay, does anyone have any questions about critical versus stationary point? I know that in your homework you will be asked about a critical versus a stationary point.